I looked up the word in the dictionary just to know whether I was up to the task. Very probably. And so this is a rant, noun, fierce, empty declamation without much meaning or dignity of thought. I thought I can do that. I should be okay. So we've got 4 talks, and they're all about matrices. You know that because it says right here, matrix. This one says matrix, this one says matrix. Now the 4th one does not because they got the wrong title, but the actual title is really cool matrix stuff. So that's 4 talks on matrices. So if you still don't know what a matrix is by the 3rd talk, the 4th one will give you a chance to catch up. Now, the first talk addresses this sort of classical problem. So you have a low-rank matrix. So think of a big, bulky thing. Being low rank, it's like a code. There's lots of redundancies. And so if you have a random entries, you should be presumably able to reconstruct it from the other thing. So this is very useful. And so it leads to the question of, given this matrix, how do you factor it? How do you express it as a product of a long, thin matrix times a wide, narrow one? Now, this is often under specified, and so you want to add all kinds of goodies that you like in the way of regularization. There's this really beautiful theorem, beautiful result in the paper that shows a strong duality for large class of non-convex such problems. Now, these are non-convex problems, but the beauty is that when you dualize it, what you get is something convex, and the duality gap is 0. So that's quite elegant. So you've got these non-convex to convex correspondence. You've got applications to classical problems like robust PCA and matrix completion. And there's also a bunch of hardness results to come along. So now that's the first paper. The second one, which is also about matrix. So that's a more sort of typically TCS paper. There's a very well-defined problem, which is you've got a matrix and you want to compute the singular values, in other words, the eigenvalues of A transpose A, and these are all non-negative values. And so you can do this with matrix multiplication, SVDs and so on. So the complexity question is, can you do better? So there's a little twist in the way they phrase the problem by instead of asking for particular singular values, they ask, well, given some interval, how many singular values lie inside that given interval? Just give me a number. Once you can do that, if you can compute these histograms, then you can do something even cooler, which is to compute like moments of all, the spectral sums. You take the sums of these singular values and you add exponents to them and that sort of thing. So they show that you can do all of that without using SVD, in other words, without using matrix multiplication, so you can beat the n to the omega bound. And this has lots of applications to things like compressed sensing and so on. A third paper, there too you take a very classical problem, which is to compute the spectrum of a Hermitian matrix. A Hermitian matrix has real eigenvalues, and so you want an algorithm that runs in parallel and is stable. The conjunction is the hard part. Stable means that you can compute over a small number of bits without too much error. And so the one really cool idea in the paper is to replace the standard techniques, which is to take power iterations or standard factorization of a matrix like QR, and to replace these by a sort of iterated complex exponentiation. Visually, you should think of this as a sort of power iterations modular, because you do this over the complex plane, circle, and so you just go around. And it's all inspired by quantum computing. I might pass my 5 minutes. Okay, and the last but not least paper with long titles and many names is the problem of analyzing alternating minimization for tensor norms over product groups. So let me unpack this quickly. So consider in 3 dimensions, you have 2 convex bodies, and you want to compute the shortest distance from one to the other. So a natural way of doing it is just take 2 points, fix one, and get the other one, and just move it as close as you can to the other one while remaining on the convex body, and then you fix that one, and you take this one, you move it, and you alternate like this. Now this could take a long time. That's the whole point, to see how long it takes. Now here we're going to do the same thing, except it's not points and convex things, and they're different objects. Okay, instead of points, what we have are matrices over special linear group. These are convex. These are matrices that are invertible and have determinant 1, so they form a group. And these would be your variables. And these guys together, as a product, act on the sort of tensor that you can form over all the sort of corresponding complex vector space. And so it's really miraculous that you could do this efficiently. So they show that there's sort of dual of that, for which there's an FP task. And then for the problem itself, they show a single exponential algorithm, which beats the previous one, which was doubly exponential. Now, what's remarkable about this paper is just the range of things that it puts together. So it extends recent advances in operatic scaling, and it's got links to everything: invariant theory, the so-called no-cone problem, quantum IT. Well, you can read this list. And this brings me to my last point, which is that 20, 30 years ago or something, computational linear algebra was a beautiful, celebrated field that was, kind of dormant. But then something happened. There's this sort of explosion of incredible results. And the cool thing is most of them really took place in theoretical computer science. And I think one reason for this is the sort of sponge-like quality. And these papers really show that that TCS is not scared to just go around and simply suck in every idea from every part of mathematics or physics that they can. That's really one of the strengths of our field, and I think this session will show that. So I will stop and I'd like to welcome the first speaker. Thank you.